Today is Earth Day, and today we are turning the sun into sound. Right? Lots of power. Okay, so let me shut that off before it nails it for copyright issues. So that's just a local radio station playing some pop music. But we are converting solar radiation into sound, obviously through electronics. And today is April 22nd, 2022, and it is Friday, which is good. And it is extremely sunny outside. So that's facing southwest. And we are, let's see, very, very bright. We have this object in the sky up here that generates energy, right? And I can collect some of that energy using photovoltaics like this. There is a system up on the roof that is generating 3,500 watts of power and selling most of it to the neighbors. Some of it runs the light over here. Some of it runs this sound system. But the energy that's making it all work ultimately came from the sun. So solar energy, we think, that's like a novelty thing. Oh, that's not. There's very little of that actually being used. Oh my goodness, all the 15-year out of date information that you find on the internet. And the fact of the matter is, I got 4 kilowatts of solar on my house, and that is about 1/1,000,000th of the amount of solar power that is in the PJM power grid in this area that basically supplies our power grid. So there's about 4,000 megawatts or 4 gigawatts of solar power being generated today on PJM in the utility scale kind of power stations. And then there's probably another 4,000 or 5,000 megawatts or 5 gigawatts coming off of people's rooftops like mine. And so that's, 9,000 megawatts of electric power being generated from the sun just in PJM. And I have about 1/2,000,000th of that at my house. So it's definitely not anything novelty. It is very much an established, blooming, blossoming industry. Being able to gather that energy that's already there and use it to make electricity. So you don't have to light stuff on fire so much. So let me put this thing down here so we can talk about the sun a little bit more, because it is such an omnipresent force in the world. I need a stand for my camera. Where can we set it? How about over here? How about right here? Okay, we'll sit it here and we will go over some interesting facts about the sun. Right? Let's put it here. Hopefully this thing holds it. Alright. There it is. So solar energy. So we got our monocrystalline photovoltaic module, miniature one here. The ones that are out on the house are a bit bigger than this. This was just a small one. But, so, the sun, it's a star, right? It's a stellar object that uses nuclear fusion to produce energy. And every day, we see it rise and set, obviously because the Earth is rotating on its own axis, and the sun is always lit up. It's just the Earth is moving. And so the sun is composed primarily of hydrogen. I think it's like 75% hydrogen and 25% helium. And of course, there's minor amounts of other elements in there, but hydrogen and helium is the vast majority of it. So the nuclear fusion process in the sun, basically the conditions in the core of the sun, so the very innermost layers of the big ball that it is, are of such temperature and pressure, both of them are important, that the hydrogen atoms can get close enough, the nucleus of those hydrogens can get close enough together that they will merge and form helium nuclei. So you take a bunch of hydrogens and you put them together and make helium. In that process, when those neutrons and protons come together in their to a nucleus of helium, energy is released. So that's nuclear fusion. We're taking small light nuclei, middle center kernels of atoms, and putting them together into larger ones, and that process generates energy up until the point of the element iron. Iron is kind of in the middle of the group of elements where fusion will produce energy. And then once you get bigger nuclei than iron, the process of fusion actually consumes energy. And whenever we talk about nuclear power plants, kind of like, and when the sun goes away here at night, I'm probably going to be getting a lot of electricity from a nuclear power plant because there's one kind of nearby. And they take big nuclei like uranium with 235 protons and neutrons in it, and they break it apart into smaller pieces. And up until from uranium going up in or down in mass, that process releases energy. So you got nuclear fusion in the sun, putting things together, and fission in nuclear reactors at power plants that people have built. So the energy that's coming from the sun, so I've generated about, so far today, like 21 or 22 kilowatt hours of electricity from the sun. And on PJM Power Grid, like I said, we've been cranking out about 4,000 megawatts, 4 billion watts of power all day long from like 9 a.m. till probably even still now. And that energy, I said it comes from nuclear fusion, but I mean the sun is really large. I don't know the numbers. I don't know how much mass it has in terms of kilograms or tons or million tons. I don't know what that is, but it's very big. Very big. If the sun is this big, the earth is like that big. Okay? It's huge. As our former president would say, it's huge. So the energy that's being generated by nuclear fusion, we think, okay, well, fusion, nuclear, anything nuclear, it's got to be like, boom, really high amounts of energy being released from a small volume, right? That's the whole idea of nuclear weapons. You have this small mass and it blows up an entire, square miles of area. But in the sun, the things are a little bit more gentle than that. And I use the word gentle, and people might be like, well, there's nothing gentle about the sun. It's 15 million degrees in the core, and it's 10,000 degrees at the surface, or if you're on Celsius, it's 6,000 degrees. How could that be gentle? Well, like I said, the sun is very large. And it's a ball, it's a sphere. So, remembering back to geometry, a sphere is the geometric shape that has the lowest surface area to volume ratio. So if you take the surface area of the sun in terms of, say, square feet or square meters, and divide that by the volume of the sun in terms of cubic feet or cubic meters, that number is, it's a fairly low ratio compared with, say, a cylinder. or a cube of the same kind of physical length, width, and height. The other thing with the sun is being that it's enormous. The bigger the shape gets, the volume does not scale up as fast, or the surface area does not scale up as fast as the volume. So if you take a basketball, a sphere here on Earth, a little basketball, and you calculate its surface area to volume ratio, that's going to be a much higher number than the sun, because the sphere is so small. And a more extreme example would be to take the surface area to volume ratio of an atom. The surface area in relation to the volume is going to be extremely high. And that is the surface area to volume ratio is one of the most critical numbers of it that you could possibly apply to a thing like a star, because that defines the rate at which energy is lost from the surface of the star. So the volume of the sun determines the power that it produces in terms of nuclear fusion. The surface area of the sun determines how fast that radiation goes off into space. So because the volume is so big compared to the surface area, the sun gets very hot, for one, because the energy has, the power that you're producing, the only way for that energy to leave the sun is by radiating off the surface, because there's no air in space for it to be carried away by air currents. Like, you blow on your hot soup here in the Earth and the air molecules carry the heat away. You don't have that in space. So the nuclear fusion that's going on in the sun, if I was to take go to the core of the sun and take a sample of that material and take 1 cubic meter of it, all right, the rate at which nuclear fusion is happening within that cubic meter of space would be like a few hundred watts. It would not be very high, okay? I think the entire sun on average has a power production per cubic meter of volume of about 300 watts. That is a pitifully low power density. Okay, a human body has a power density higher than that. So your body heat that you're producing from metabolism, if you were to take the volume of the power, 100 watts of, say, 100 watts of heat, over the volume of a human body, it's going to be greater than what is being produced in the sun by nuclear fusion on average in that whole sphere of matter. That's an incredibly interesting concept, because you look at this star and it's emitting enormous quantities of energy, something like 10 to the 24 joules or watts of power in the form of radiation, light and heat, thermal radiation, all the different kinds of radiation that come from the sun. And that density at which that energy is produced is incredibly low, because it's such a large volume of space. You have so much stuff in which to run the nuclear reaction. So it is a very slow kind of smoldering nuclear fusion that goes on in the sun. But by the time that gets out to the surface, it's very, very high temperature. It's 5,000 degrees Celsius. And that radiation comes off the sun and it goes out into space, and we get it here, right here. And I can actually feel heat. And the solar radiation at the surface of the Earth turns out to be about 1,000 watts per square meter. So that means if I have a solar panel that's 1,000, or it's 1 square meter, there's 1,000 watts of solar radiation hitting that on a good day, a nice sunny day, and the solar panel can convert maybe 20 to 22% of that into electrical energy, right? And that's pretty good because go back 20, 30 years and that number was half. So obviously we have a slow smoldering of nuclear fusion in the sun. Hydrogen atoms are merging with each other and forming heliums at a very leisurely pace per cubic meter. But there are a lot of cubic meters in the sun. So at the end of the day, you're consuming many tons of hydrogen per second are being fused and produced to form helium, and energy is being released at the rate of 10 to the 24 joules per second. A lot of power. Many orders of magnitude more power than obviously people could ever use. We receive on Earth, I think it is 174 to the power of, it's petawatts, power of 15, right? From the sun, on average, for across the entire Earth. So we get a small quantity of the total. The thing that's interesting about a star like the sun is the nuclear fusion only really happens in the middle, in the core, in the innermost layers of the star, because the pressures and temperatures are high enough. So out at the surface, it's not hot enough, and the gas is not dense enough because the gravity compresses that gas under its own weight, which is the entire thing that makes a star start fusing hydrogen. Is the gravity takes all that gas from space and it compresses it down, and when you compress a gas, it gets hotter, and the temperature goes higher and higher and higher as the mass gets larger, and eventually you reach just ignition temperature and fusion starts. So fusion's kind of smoldering along in the core of the sun, and all that gas is very high density is there, and that energy eventually finds its way out to the surface. Right, so right now I'm getting energy here. I just used it to power that radio or the stereo. I feel the heat. Is this energy immediately a product of fusion? We all kind of learned that it takes about 8 minutes for electromagnetic radiation or light to reach us from the sun over the 93 or so million miles that it is from here to there. 8 minutes at the speed of light. So did fusion 8 minutes ago create this radiation? And the answer is no. So the light that's leaving the surface of the sun had to first, before it leaves the surface, it had to have traversed the entire radius of the sun. So the sun is very, very large. Like I said, I don't know the number, but it's many, very, very big. It's a huge volume of space. So all that fusion that's going on in the middle, when the energy is released from the hydrogen atoms coming together, it throws off gamma rays, it throws off, particles, various subatomic particles that have a kinetic energy to them. And that kinetic energy hits other atoms that are in that volume of space. It kind of slams into each other and everything starts vibrating. And that's heat. That's thermal energy. The definition of heat is vibration at the molecular or atomic or subatomic level. And that heats the gas up and keeps it hot so that fusion can continue happening. But that energy that it jostles itself around, and all those atoms and all those things that are in there, they just kind of bump into one another. And statistically speaking, a unit of energy from the core or the center of the sun, it takes about 100,000 years for that packet of energy to reach the surface and then fly off into space at the speed of light. So the reason is the sun is so dense that the uh, the, the material that's in there constantly, the stuff is constantly pounding into each other. It goes this way, then it goes that way, then it goes this way, then it goes that way, it goes this way, it goes that way, and it's like a randomized. Think of like those lottery machines where they have the balls and they're going all over the place. The balls are hitting each other and the energy's going everywhere. But because the energy is being generated in the core and space is cold, the general tendency is for the energy to migrate towards the surface of the star. But it takes, because the star is so big, the sun is so big, it takes about 100,000 years for your statistically average packet of energy, your joule or kilowatt hour or whatever your favorite unit is, to get from the middle to the outside and then zing off into space. And then take 8 minutes and maybe some of it will come to Earth, and a very, 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 very tiny fraction will strike one of these solar panels and then set some electrons in motion and, you know, maybe charge somebody's phone or run a light or cook your dinner or whatever it might be. And then the energy goes into the atmosphere just like it would have as if the solar panel was never there. So that's the story of the sun. How energy gets from the middle of it to the outside is a long, arduous process. So the light that we're seeing here was actually generated on, you know, the average particle of photon of light was actually created at the dawn of human civilization, you know, 100,000 years ago. Long before any, you know, prehistoric kind of time. So that's pretty interesting fact about the sun. And I would think that a bigger star would take even longer for that to happen, because it's just bigger, more, there's a larger radius for the energy to pass through. That's it, you know, more than enough energy than we could ever dream of using. And we have the technology to harness that, so we don't have to keep burning things and generating all kinds of chemical byproducts. The entire premise of Earth Day, right? Avoid the massive releases of unwanted stuff into our environment that causes us problems, for whether it's people or anything else. That's it.